I think I see much more people today than the past class, but I am in the middle of a class, so if you miss the previous one, it's going to be tough. So I will try to summarize a little bit what is going on, but it's going to be tough, because I've been talking for like 35 minutes about this stuff. So I start somehow from the beginning, from the first slide, and I will go quick to the point where we were at the end of the last class. Okay, so the issue is the design of small hydropower, and in particular the, I would say, complete analysis of profitability and impacts associated to the design. In particular, with reference to the choice of the capacity of a small hydropower plant, which is the maximum discharge that a given plant can process. Okay. The main focus of this course is the design of small hydropower plant in mountainous region, where you have some intake and some outflow, and they are separated apart several kilometers. This is done because typically the stream flow is pretty low, but the head is very large because the elevation of this point and the elevation of this point are very different. So, provided that the power is a product between discharge and head, in this case the discharge is limited, but the head is huge, let's say more than 100 meters or so. This is the type of thing that a small hydropower plant produces. This is upstream natural flows in the absence of this of the plant. This is what you will see in the stream throughout all these reaches. But downstream of the plant, that is this plant here, this is what you actually see. And this is continuously in space for several kilometers. And in many cases, as I will be showing you in a while, you have many small plants in cascade. So downstream of the outflow of this plant, you have another small hydropower plant, producing more or less the same type of effect. Okay. One of the key points about design of small hydropower is the estimate of the flow duration curve. So what are the water resources available in the river? Why? Because you don't have storage in this case, so you have to process essentially what you have in the stream in that moment. So it's very important to understand what is the discharge in the river, because this is a big constraint on the discharge that the plant can process, and therefore the amount of energy, the power that you can produce. Now, let's assume that we know the flow duration curve at the intake, which means that we know the frequency distribution of the discharges available in the stream, and let's try to find out how we can relate the energy produced by the plant to the stream flow available in the stream. So the first thing, the first equation through which these two things are related is the equation that you see here. Essentially what you have to do is to integrate through time the product between constant, the head, the efficiency of the plant, and the discharge. So essentially in this integral we are summing up the energy produced during day 1, day 2, day 3, day 4, day 5, and so on. And we integrate through time, summing up all the powers produced day by day across a given period, 10 years, 20 years, 30 years, whatever. Okay? In the second integral, which is actually exactly the same expression in a different fashion, we are again integrating, but in this case we are integrating through Q, meaning that instead of summing up the energy produced during day 1, day 2, day 3, day 4, day 5, we sum up across all different flow magnitudes, meaning the energy produced when Q is low, intermediate, high, super high, and so on. So we span all the possible values of Q and we sum up, because actually the variability of the energy in a given day is only due to the value of Q in that day. Okay, so if you keep all the days in which you have 10 cubic meters per second in the stream, in all those days you will produce the same amount of energy. So it makes sense to sum up across all the possible values of Q. And provided that you are summing up over Q, it's very important to weight properly different Qs depending on the frequency. So you multiply Q in the integral by PQ to say how these contributions are important. They are important depending on how frequently you actually observe that particular value of small q in the stream. Okay? So you sum up all the different flow ranges, taking into account the relative probability associated to that, to the different flow ranges. And this is what you see here. This is a simplified expression because we are assuming that H, the head, and the efficiency eta are constant. But for now, that's fine. Of course, in this case, when you integrate over Q, you have to multiply the whole expression by the overall duration of the period that we are taking into account, which is typically the duration of the incentives that are guaranteed by the state. So 15, 20 years. Because here no one is telling you, I mean, this is the relative frequency, so relative number of times in which you see a given value of small q, and to actually calculate the energy, you have to multiply by the duration. If the energy produced in 10 years is 10 times the energy produced in 1 year. Okay, so you have to multiply by the overall duration, because here you don't have information about how many years, how many days, only the relative proportion. Okay. Essentially, we have physical constraints on that, related to the fact that you have to decide what is the range of flows that you can process. How this is established? This is established by the capacity, capital Q of the plant, that is the maximum flow that you can process, and the cutoff flow QC, that is a fraction of capital Q. So the ratio between these two guys is almost fixed, and it's a matter of the efficiency of the turbine. So let's say that for constructive reasons, QC is 20% of Q, which means that I select a capacity of 1 cubic meter per second. I will be able to process only the flows between 200 liters per second and 1 cubic meter per second. If I multiply by 10 the capacity, automatically this means multiplying by 10 also the cutoff flow. Okay? So the bigger the plant, the more you move on, this line on the right, and accordingly also the left blue line is moving on the right with the same speed, with a similar speed. Okay. Okay. So this automatically translates into a change in the extremes of integration. You are not actually processing all the flows between 0 and infinity. You are only processing the slide between QC and Q, which is dependent on the capacity capital Q of the plant. And this is how you combine together the flow regime, PQ, the flow duration curve, the frequency distribution of the discharges, and the design variable, the size of the plant, capital Q, all together in this expression. Okay, so I like this much better than this because here the capacity is somehow hidden. Okay, in this case here it is explicit and you can actually visualize what is going on. In this case you are processing all these flows. This means that the plant is too large to process this value of Q, and the plant is too small to process this value of discharge. Only that slice. Okay, now there is a complication related to the fact that the efficiency is not constant. The efficiency is typically dependent on the ratio between the capacity, the processed flow, small q, and the capacity of the plant, capital Q, according to this plot. So in this case, that is a typical case that you can associate to Pelton turbine. You assume that if the discharge is high enough, the efficiency is maximum and constant. And below a certain threshold, let's say 40% of the capacity, you have a decrease, a drop in the efficiency, because the flows are not high enough to maintain the functioning of the turbine in a proper way. So the speed of rotation of the turbine is not the optimal one, and this increases the losses due to many other factors in the conversion of potential and kinetic energy into mechanical energy and then power, electrical energy. Okay, so in this case, you can also see that it's like saying that not all the flows count equal. because this slice, the green one, is processed with the maximum efficiency, let's say 0.85. These flows instead are processed with a smaller efficiency, down to 60%, 0.6. Okay? So it's not the same thing, because you would like to process everything with the most high efficiency, the highest efficiency that you can get from that plant. So the selection of the capacity of the plant should also take into account that when you select the capacity, automatically you also decide what is the fraction of stream flows that are processed with a suboptimal capacity, a capacity that is smaller than the maximum possible value. And in this particular case, you see what happens. The most frequent stream flows are kind of processed with a not optimal, or very close to be not the optimal capacity, because the orange slice has a relative frequency that is not negligible at all. Okay. Okay, the word plus atom that you see here is only representative of the fact that when you have available in the stream more than the capacity, you process only the capacity, and the residual fraction, that is the overhead, to give it a name, is just left flowing in the river. So there is this atom is representative of the energy that you produce when you can actually drive to the turbines the maximum capacity of the turbines themselves, the maximum capacity of the plant. And this happens for a certain fraction of time. How many times? In relatively speaking, so in terms of a relative number between 0, never, and 1, all the time, it is the area of the tail of the frequency distribution of the discharges on the right of capital Q. So this area here is the relative fraction of time during which the plant is working at the maximum capacity, because in the stream you have more than enough. Okay? Clearly, the larger the plant, the larger capital Q, the smaller the number of times that the plant will work at the maximum capacity. So, as I was discussing at the end of the past class, essentially you have a trade-off going on here. You could say, okay, I want the plant to work at the maximum capacity most of the time. So if you want to do that, you actually say, okay, I'm doing a very small plant. If I'm doing a very small plant, the capacity is relatively small, let's say here, and for 60% of the time, I will be working at the maximum capacity, which is good, because this means that I'm exploiting the capacity of the plant, right? But as you can see, if you do that, you see that, the medium flows and the high flows are not processed. So it happens very frequently that in the river you have 10 cubic meters per second and you can only exploit 1. So it's a pity. And this is maybe not the optimal solution, because you have in the river more water and you are not exploiting that water. But on the other way around, if you decide to increase the capacity capital Q and make a very big plant, like in this picture here, okay, in this case, as you can see, it happens that you are able to process the high flows, almost all, and the medium flows. So it's going to be maybe a better strategy. However, in this case, as you can clearly see, you don't process the low flows, which means that for a certain percentage of time, you are switching off the plant because you don't have enough flow in the river to sustain the energy production, meaning that what you have in the river is less than the cutoff flow. So you don't have 20% of the capacity and you cannot make the plant working. And this happens for a certain fraction of time that is not negligible in this case. And moreover, it happens clearly in this way that the most frequent stream flows are processed with a suboptimal capacity, because the ratio between Q and capital Q for the most likely flows here is low, lower than the maximum efficiency, because the plant is very, very large. So when you have these stream flows in the river here, the ratio between the stream flows and the capacity is not large enough. Okay? So maybe also in this case, this is not a good strategy to exploit at best water resources available in the stream. And you have to find out an optimal combination between the two things. So graphically speaking, you should have to place your window Q and 20% of QC in the proper position. Not two on the left, not two on the right. Okay? Okay, there is an extra complication on that is maybe difficult to visualize from the viewpoint of the equations, but it's very easy to understand from the physical viewpoint. If you have 1 cubic meter in the river, 1 cubic meter per second in the river, can you actually take 1 cubic meter per second out of the river? No, because if you do that, downstream of the intake, you don't have nothing. So every time there is a minimum flow discharge that has to be released downstream regardless of everything. Okay, what is the implication for that? In general, the stream flow processed and the stream flow available upstream, they are not the same. So given that, I have to use two different letters. One quantity is the stream flow available in the stream, small q. A different thing is going to be the stream flow taken out from the river and diverted to the plant, which is called QW because it is the worked flow or the workable flow. And in terms of the equation, QW, so the flow that can be taken out and given to the turbine, is the stream flow available in the stream, small q, minus the minimum flow discharge. So that equation simply says that what I can actually process is not the entire stream flow available, but the stream flow available in the stream minus the minimum flow discharge. So every time there is a translation relating QW, the flow that you can process, and the natural stream flows upstream, small q. Okay, remember that capital Q is the capacity. Small q are these charges. So capital Q is a constant. Small q is a function of time. And QW is a function of time accordingly. Never get confused about that because otherwise it's a mess. Okay. In fact, small q is inside the integral, and capital Q is the extreme, the constant. Okay. This is local in time. What is so it is true time by time, day by day, minute by minute. What are the implications in terms of probability density function? Because now my integral is expressed in terms of probability density function of these charges that you can process in the plant. So forget about the analytics of that. Look at the picture. Let's assume that you have incoming flows given by the dashed line. What is how this frequency distribution of the natural flows, how this is translated in terms of frequency distribution of processed flows, QW, simply a leftward translation by a quantity minimum flow discharge. If in the stream you have for 30% of the time 1 cubic meter per second, but you have a minimum flow discharge of 100 liters per second, the frequency that you associate to 1 cubic meter per second available in the stream is automatically translated into the same frequency of 0.9 cubic meter per second diverted to the plant, because automatically you subtract 100 liter per second that you have to release downstream. So there is a one-to-one correspondence between the frequency of Q and the frequency of QW only through a translation on the left. Did you get the point? So the dashed PDF is what you have available theoretically, but provided that you have to leave to the stream some water, you have to translate this guy to the left by a quantity that is equal to the minimum flow discharge, to actually keep track of the fact that some water has to be released downstream of the intake regardless of all the other conditions. Okay? So from the viewpoint of producing energy, a quantity equal to MFD, it's like not being actually in the river. It is there, but you don't have to see it. You don't have to consider it. So this subtraction that you see at the blackboard is translated into a translation of the frequency distribution to the left. Okay. Okay, so this is the last constraint. You also clearly have to include the effect of the minimum flow discharge. And what you do from the viewpoint of the analytics is to change this new variable QW and get this relationship between QW and Q, and the PDF of QW and the PDF of Q according to the picture. Okay, so this is how the plant works. This is the final expression for the energy. It is simply a nice, elegant way of considering all the processes I have been talking about. So the presence of a maximum size of the plant, the presence of a cutoff, the variability of the efficiency of the plant depending on how much you process, and the minimum flow discharge altogether. So how can we actually select Q so as to maximize the energy produced by a given plant? We have to maximize this function. Okay, this is a scheme that is maybe useful to single out 3 different cases depending on how much stream flows are available in the stream. Maybe it's good to try to visualize what is going on. In the right case, the plant is switched off because you don't have enough stream flow in the river. What does this mean? This means that the small q, what you have in the stream, is smaller than the sum of the minimum flow discharge and the cutoff flow. So you don't have enough stream flow to guarantee at the same time the minimum flow discharge and the minimum flow that you need to activate the turbine. Consequence of this, you switch off the plant. You can. Right conditions. In this case, the processed flow QW is 0, and what you release downstream is exactly the same that you have upstream. It's like not having the plant because the plant is switched off. Okay, then there is the opposite case in which you have in the stream more than the sum of the capacity of the plant and the minimum flow discharge. This means that you have in the stream enough water to give to the plant the maximum water that the plant can receive, plus the minimum flow discharge. That is what you have to release downstream by law. Okay? You have more than that. What happens? The exceedance is just released downstream because you don't have any chance to process it. Your plant is physically bonded and the capacity is met already. You cannot process more than that. So in this case, the plant is functioning at the maximum load, meaning that you are processing energy in correspondence of the capacity of at the maximum capacity of the plant. The diverted flow QW is capital Q, the capacity, and the exceedance with respect to the capacity is released downstream. In the green case, it's an intermediate condition in which you have some water, enough water to switch on the plant, but not enough water to make the plant working at the maximum capacity. This means that you release downstream, green thing here, the minimum flow discharge, and what you have on top of this is diverted to the plant. Capital Q minus minimum flow discharge. What is arriving minus the minimum flow discharge that you let flow downstream, that is what you actually process. So an intermediate situation. Okay. Now, beside the analytical expression that is, I mean, to me it's useful, elegant, and whatever, very clear for engineers, but if you miss some details about the mathematics, it's not that relevant. The point is what you have to know if you want to address the question, what is the optimal capacity, what is the selection of capital Q that allows you to maximize the energy production. And the type of information is written in the equation. You have to know the stream flow frequency distribution at the intake, the water resources available. That's what this course is about. You have to know the hydraulic head. Okay, that's complicated or easy depending on the cases. Okay, it's very easy. A first order approximation is the difference in the elevation between the intake and the outflow. Okay, this is the correct answer. No, you have to take into account energy losses in the pipes, blah, 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 flow condition, Reynolds number. Okay. If you have 300 meters of head, the net head is going to be 285. Okay, so you can do the calculation. The hydraulics is beautiful because everything is clear. You have the equations, you calculate. It depends on the size of the tube, right? So the larger the tube, the more expensive, the smaller the velocity inside the tube, so the smaller the losses of energy in the plant, which means more energy produced. Clear? More expensive, more energy. Okay. First approximation, capital H, difference in elevation between the intake and outflow. Not the perfect answer, more than enough for the goal that we are seeking now. Okay, and then the efficiency. Of course, we have to, the efficiency enters the expression as we have seen. What does knowing the efficiency curve means? Knowing the type of turbine, because different types of turbines, in fact, they do have different efficiency curves. Okay? And this is, in fact, that's why the selection of the type of turbine is associated with the stream flow regime. If you remember, in one of the previous slides, I was mentioning that stuff. Because in certain cases, you seek for turbines with a very high efficiency, maybe the highest, only in a narrow range of stream flows, because you know that more or less the stream flow available in the river is the same. So you don't care about what happens when the discharge is different than the design flow, because you know that 90% of the time, more or less, you will be around that value. So you're more interested in the local efficiency and not the global efficiency. But in other cases, you know that in the stream you have a wide range of stream flows. And the stream flow can change suddenly by orders of magnitude. So in that case, you are more interested in selecting a turbine that is able somehow to maintain the efficiency relatively high in a broad range of stream flows. So maybe the peak efficiency is smaller than before, but you have a relatively good efficiency for various discharges. High, small, medium, and stuff. Okay? So type of turbine and related efficiency curve. Given that, to me, the selection of the plant that is typically done with a rule of thumb is nothing more than a rigorous optimization problem with 1 degree of freedom, the capacity of the plant. If you want to maximize this function E, you have to calculate, the derivative and set it equal to 0. Where you have the derivative equal to 0, that is the maximum point. Okay, so this is a real-world example taken from a subcatchment of the Cava River. Flow, probability density function. The dashed line is the natural river. Then there is a translation related to the minimum flow discharges. Okay. Now I will show you different. Okay, these are the features. The area of the catchment is 10 square kilometers. The mean stream flow is a little bit less than 400 liters per second. The minimum flow discharge is 50 liters per second. The age is about 300 meters. And you have one Pelton tubing, a single Pelton tubing. I will show you graphically how the energy is changing for different values of the capacity of the plant. So we start with a relatively small capacity, as you can see. Okay, that is the maximum flow that you can process. This means that 70% of the time you are working at the maximum capacity, but as I was saying before, you're also missing some low flows here, and overall you are missing medium and high flows. The energy that you can produce is about 3.5 gigawatt hour. Now you increase the capacity of the plant up to I would say 0.55 cubic meter per second. So this is the cutoff. This is the range of flows that you actually process with the plant. You see, now the energy is almost 6 gigawatt hour every year, which is significantly higher, almost 2 times. Okay, now you further increase the capacity up to, I think, close to 1 cubic meter per second. Sorry, 1.5 cubic meter per second. So very, very high. This is the range in blue. You see the range of stream flows that you are able to process. Clearly, provided that the plant is very big, when you have only 200 liters per second in the stream, you cannot activate the plant. So you are not processing the low flows because the plant is too big. As you can see, now the energy that you can produce is back to 4.3 gigawatt hour per year. So a significant drop compared to the previous case. Okay, so if you know all these elements, using this equation, you can calculate the energy associated to different capacities and find out in an objective way what is the optimal value of Q, not relying on your previous expertise or strange procedures, but only relying on objective quantities, physical quantities, numbers. Okay, so that's the point I would like to make. The selection of the size of the plant depends on a number of intertwined factors: flow regime, type of tubing, head, efficiency curve, blah, 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 everything that was listed before. And this is something that can be quantified by engineers into numbers and find out the optimal number in those conditions. Okay. Well, next step. Now let's think about the real-world problem. And the question is actually the energy the quantity that you want to maximize, the energy produced? No. No one cares about the energy. Everyone cares about the money. Why the money is relevant here? Well, not all the plants, they cost the same. The bigger the plan, the more expensive. So clearly there is a trade-off, again, not in terms of energy produced, but the revenues that I get, taking into account the expenses and the inflows, the money that I earn and the money that I have to spend. So it's an economical evaluation. This is a nice example of application of economical concepts. Okay. Essentially, the problem behind this is the economical fluxes are observed in different times. Okay. So if you want to do a serious or a kind of serious economical evaluation of a project, you cannot just sum up and subtract revenues and costs like if they happen at the same time now. You have to take into account when. And particularly in this case, what you have to expect is to have most of the costs to be sustained now, and the revenues coming from the energy selling coming in year by year for 20 years, 15 years, the number of years for which you have incentives associated to the energy. So that's the economical plan that you have to do. Essentially what I'm saying is that it's useless to make a very big plan to produce more energy if in the end, to build a very big plan, I have to spend more money, and the trade-off between what I have to spend more and what I get more is negative. It's better to do a smaller plan. So the question is, how much? What is the number from the engineering viewpoint? Okay, if you want to solve this problem, we have to set the problem mathematically because we are engineers. Okay, so revenues. What is the revenue that you get during the year K, where K is a number between 1 and 20 or 15? So the generic year during the project. Very easy. The revenues are proportional to the energy produced during that year. So RK is proportional to EK, function of the capacity, and the conversion factor is the price of energy, EP, because the price of the energy for run-of-river hydropower plants is constant and fixed. Once you get the approval, you know that the price of the energy will be 0.22 kilowatt hour from the moment you switch on the plant and for the next 15 years or 20 years. So EP is known at the moment of the approval of the plant, final approval of the plant. Okay. That's the equation-like version of the statement that I did in one of the previous classes when I say clearly, if in the meantime, when you are trying to get the approval, they change the law and they change the price, EP, then everything changes. This is how this happens. Okay, so the revenue during the first year is going to be the energy produced during the first year times the price of the energy, EP. And the energy produced is a function of the capacity, capital Q. And provided that the energy is function of the capacity, as I've been showing to you before, also the revenues are dependent on capital Q, the capacity of the plant. And this is true at the year number 0, 1, 2, 3, 4, 5, 15, or 20. Okay, should I now sum up the revenues of all years in a standard way? No. No, because the revenues for the first year will be observed after 1 year, and the revenues during the second years will be seen only 2 years since the switching on of the plant. And the revenues of the third year will happen later and later and later and later. Okay, I'm not very titled in teaching you economics, but even me, I'm able to understand that maybe some money in the future is not the same thing as take some money now. So there is a risk associated to that, which means that the later, the less is the value associated to the same amount of money. Okay, that's the idea of this equation here. The idea is, if you come to me and say, here, take 1,000 euros, this actually has a value of 1,000 euros. If you come to me and you say, okay, maybe in 3 years, or maybe you say for sure, but I'm thinking maybe, for sure I will come here in 3 years and will give you the same amount of money. Now the value of 1,000 euros maybe in 3 years is less. Let's say 800 euros. Okay, so you cannot make comparison and sum up. And this is exactly what you do here. You sum up and you discount the future revenues, and you discount more the future, the more they are supposed to happen in the future. According to this formula, where K is the year, meaning that the discount factor is 1 for the time now, 0.96 after 1 year, 0.92 after 2 years, 0.88 after 3 years, and so on. Okay? So let's assume that every year you have the same frequency distribution of the discharges, the same energy produced. When you translate this into revenues, you cannot sum up. You have to sum up, discounting the future fluxes according to this progression. These are example numbers that are derived assuming a discount rate of 4.5%, which is a reasonable value for the discount rate of some financing or some the type of discount rate that you get if you go to banks. Okay. Okay. Did you get the point? So of course, if you increase R, the decrease of the discount term is going to be sharper. If you set R equal to 0, you will get 1 throughout the entire term. This means that you're somehow very convinced that you will get that money in the future. But this is not in general the case. It might happen that everything breaks, that the river dries out, that you get an earthquake and everything, I mean, many possible things. So societal conflicts, and Italy leaving the European community, and the incentives you don't have enough money to do that, and many variables. Okay, that's the idea. Okay, so this is the formula for the total revenues. You're summing up the annual revenues, properly discounting the future economic fluxes. Okay. These are the revenues. Now let's talk about the costs. Okay, in terms of costs, you have 2 types of costs that you have to face. The cost analysis of a project of this type is very complicated, because you have many different things: the hydraulic thing, the tubes, the pipes, the sensors. You have the concrete thing that you have to build. You have the technical thing related to the energy, the transformator, the tubing, and all that stuff. So you have many items. So I'm just proposing you a very quick procedure. Of course, if you are willing to apply this technique to real-world project, you have to do a serious cost-benefit analysis and make an item list with all the costs and try to get some reasonable number. Okay, this is just for the sake of the homework, to avoid you becoming crazy with searching catalogs and finding out how much a turbine and so on. Okay, it's going to be very time consuming for you. Okay, construction costs. I'm proposing you this formula. The idea is the larger the plant, the more expensive. according to some power law, where the exponent b is smaller than 1. Okay? This means that if you double the size, you double the capacity, the cost is doesn't have to be multiplied by 2, but by 1.4. Okay? Plus, you have some management costs. The management costs are different by the construction costs because they don't have to be sustained only at the beginning of the project. But you have to sustain management costs every year. Why? You have to pay some money for a small hydropower plant year by year. What are the possible reasons? Okay, annual water abstraction taxes. This is very interesting, actually. The municipalities hosting the people complaining about the small hydropower plant, they complain, but at the same time they say, okay, you can, at some point in the authorization process, they say, okay, you can build it here, but you have to give me like 3% of the money that you get. Okay, so you have some taxes that you have to pay to for the water abstraction that are typically released to the local municipalities, of the order of some tens, thousands of euros per year, not so cheap. Maintenance, ordinary and extraordinary. Something breaks, okay, you have to replace it. Big flood, destroying the pipes or destroying the intake, the withdrawal, you have to repair. And many other things that you have to double check to guarantee the functioning of a power plant that is a very complicated machine, indeed. Okay. Typically, the operation and management costs are less dependent on the capacity of the plant, for clear reasons. Okay, why I would like to distinguish between operation and management costs and construction costs, because the construction costs are sustained at the beginning of the project, so you don't have to apply the economical rule of the transfer through time of the economical fluxes. Instead, the operation and management costs, again, likewise the revenues in the future, they are maybe costs or maybe not. You are lucky and you don't have to maintain, or I don't know, for some reason you don't have to pay the water abstraction taxes, or I don't know. So if you now sum up everything in this economical indicator that is used very frequently in economical evaluation of environmental project, that is called net present value. And you get this formula. I will go through the formula in a while. What is the net present value? What is the meaning? It's the problem is that you have a sequence of cash inflows and outflows, meaning money that you get and money that you have to spend, distributed through time. You calculate the net present value of that project consisting on that those foreseen money fluxes as the sum of every cash flow properly discounted back to the present value now. So applying the discounting rule, for which when you transfer future fluxes of money, plus or minus, back to the present, now you have to apply this conversion operation. The discounting, reducing the actual value of those future fluxes, reducing the future costs and reducing the future revenues. So from the viewpoint of the small hydropower plant, the net present value is a function of the capacity, because it is the sum of these two terms minus construction costs that you have to face now, plus the sum in the future for the next 15 years or 20 years or the number of years for which you are sure that the incentives will apply, of the discounted difference between revenues and costs in the future. So RK are the inflows and CK are the outflows. And both of them have to be discounted to their present value, applying to this 1 over 1 plus R to the k power term. That is by definition smaller than 1 because R is positive. Okay, here you see the typical plot that is presented in these economical evaluations. The histograms are the annual cash flows. So the cash flows plus minus pertaining to year number 0, 1, 2, 3, 4, and 5. And the continuous red line is the net present value after 1 year, 2 years, 3 years, and up to the final value of the project, in this case 20 years. Okay, so in the first histogram you see what you have to spend to build the project, to build the plan. Now, in this case, 1 million euros. Then you see that you get some positive fluxes, meaning that the difference between the revenues from the energy selling and the maintenance cost is positive. You see that this is about, I would say, 150,000 euros per year. This is, as you can clearly see, decreasing because you have to discount this. So what is going to happen at year number 1 is more important, weights more compared to the same amount of money that is foreseen after 20 years, according to the increase of discount factor. And you see that at the end, summing up all the positive blue things, you compensate the initial investment after 6 years from the investment. This is actually crazy. You don't have financial tools where you actually are able to recover the initial investment after 5-6 years. It's totally crazy. And okay, pretty interesting here. At the end, the net present value, that is a measure of what you get, it's 1.5 million euros. So in 20 years, you get 150% of what you put initially in the investment. Okay, this is an example, but these are realistic numbers, at least using the previous incentives. And this is the reason for which we experienced a boom of small hydropower plants in Italy, in all places, in all countries. Okay, and once you get the authorizations, this is essentially certain. I mean, the uncertainty associated to that, where are? The price is constant and defined by law. Extraordinary events like collapse of something, but I mean, very unlikely. Maybe in some years you get some extra maintenance costs. You have to repair more frequently the things, but I mean, it's not a big deal. Well, the only problem, maybe, is the estimate of the capacity. So the real drawback of the procedure is you have to be sure that the frequency distribution that is hidden behind E as a function of Q, this equation here, is actually what you believe. And remember that you don't have measurements about that. So you have somehow to trust your model. So the big uncertainty is associated to the estimate of water resources. Very, very interesting. Why it's interesting? Because typically the people handling this project, they don't know the hydrology at all. So it's like looking for the source in the literature, the best formula in the literature when you propose a plan that give you the best answer in terms of energy, which means that among all the possible sources and the possible methods, you will be tempted to select the one providing you more discharges in the stream, because this will eventually turn out in more energy, and through all this system, more net present value. Correct? I am a designer. I want to tell the people that is giving me money, this is a super deal. You will get 2 million euros. So now everyone knows when we do projects, we have options. Okay? The people I'm talking with, they don't know nothing about hydrology, so I select maybe a different method. And so using this method, I can tell you we get 2 million euros, not 1.5. And maybe looking in the literature, we found out a third method giving 2.3, even better. No one will check out. You can't. You need 1 year, maybe 10 years to do the statistics. Okay? So be careful. The choice of the capacity is the entire ball game. So this story was taught to you to give you a precise idea of the link between flow regime capacity and optimal capacity and the economical value of the plant. So clearly the thing is very, very tricky. You have a place without measurements, so no one is telling you you're right and you're not right. So every opinion is good. I will somehow sell you a project telling you that you will get 2, 3, 4, 5 millions of euros out of this river. You take it typically, and then you sell it again to someone else, because there is a chain of selling of plants of this type. I try to do the things very quick because I don't want you to realize the numbers are not exactly the numbers that I have put in my project, but after that, I'm done. Okay, so these are the things how they work. From the viewpoint of the engineers, the new selection of the optimal capacity is as stupid as before. The only thing that you have to do is to replace EQ with NPV as a function of Q. Again, you have to maximize a function. It's something that you can solve in 5 minutes. You calculate the net present value for different values of the capacity, and you find out the optimal one. What you have to know to do this calculation, besides the equation: the flow regime, the environmental prescription, the minimum flow discharge, and also the technical features of the plant and the economical issues. So everything together in a robust mathematical formulation ready to use. Of course, this is just an example. You have many, many variations on the same thing. For instance, up to now, I have assumed that I put all the money at time equal to 0. But typically, this is not the case, which makes the thing even more interesting to me. Because the people initiating the initiatives, typically they do have 0 money. They actually sell empty boxes. So they go to the bank and they ask for some money. And they do some mortgage, and then they start the thing. So they don't sustain the cost at time t equal to 0, but they get a mortgage and they try somehow to fit the 2 economical contracts with the bank and with the seller. Okay, so of course you have to change this stuff if you don't sustain all the costs at t equal to 0, but you sustain the cost in a delayed way using some economical tool. Okay, please look at the plot that you see on the right bottom corner of the slide. The red thing is the cost of the plant as a function of the capacity. The higher the cost, the higher the capacity, the higher the cost. The green line is the revenues that you get for different values of the capacity. Same shape as the energy. So you grow initially and then you decrease. You decrease because at some point, if you do the plant too large, you are processing the most likely flows with a suboptimal capacity, and you are missing the small flows. And when you combine the two things together, you get a optimal capacity that maximizes the net present value, that is the sum between the difference between the revenues and the costs. And okay, provided that the costs are every time larger than 0, by definition you are sure that the optimal capacity from the viewpoint of the net present value is going to be smaller than the optimal capacity from the viewpoint of the energy. The two things, they are going to be equal only if you have no costs, okay? Because in this case, the net present value and the energy are by definition the same. It's just a matter of comparing this equation, the one that you see here, and this equation here. If you have no cost, the two equations are actually the same, so the optimal value is the same in both cases. As long as the costs are minus sign in this case, you get a picture of this type with the optimal capacity associated to the net present value that is by definition smaller than the optimal capacity from the viewpoint of the energy. Okay, and this is the real thing that you want to maximize. Be careful because small variations, big numbers. So you change the capacity by 100 liters, the net present value could change by 300,000 euros, something like that, because it's very sensitive, as you can see from the curvature of this guy here. Okay, here there is an example, the same question as before, assuming management costs that are 5% of the construction cost. You see that the maximization of the energy is obtained with a capacity of a 0.57 cubic meter per second. But if you reduce the capacity to the optimal value for the net present value to 0.47 cubic meter per second, you get a net present value of about 11.8 million euros in this case. Okay? 11 million euros. This is a little bit bigger than the one I considered before. So more money to invest, like 5-7 million euros to build it. Okay, so other interesting thing, there is a gap between the optimal, energetic optimal, and economic optimal. So very interesting thing, actually we are trying to maximize the exploitation of water resources, sustainable, blah, 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 but at the same time, the policy is actually telling you what is the degree of exploitation of water resources that is actually perceived by the designers. Okay? If you change the price of the energy, you change this gap in an invisible way, I would say. It's gonna be better to have, okay, the larger the cost, essentially, the larger the gap between the two. The same point I was making before. And open question, it's better to have like 10 small plants, maybe underexploited, meaning that you could get more energy from those plants, or 3 of them fully exploited, producing all the energy of the other 10s. What's best? Very different to, very difficult to address this question. So maybe even useless, but it's interesting to me. Because we take the risk of having many plants underexploited to some extent in relation to the underlying policy in a very mysterious way that you cannot control. Why this point is important? Yes, at that time. Okay. Compliments about the proposed methods, not particularly relevant. Well, the point is, instead of selecting by experience or with a rule of thumb something, this is a very interesting engineering problem that based on the data you derive solutions. So to me, it's like crazy, provided that if you miss the capacity, you can get different revenues by millions of euros. It's crazy to decide these variables based on experience or based on mysterious estimates of the flow duration curve. It's a very interesting engineering problem for hydrologists. So that's the field where you can say, I know the correct answer more than all the other guys, more than all the other engineers. Okay, here there are some examples about scenarios. If you have a mathematical tool, it's easy to run scenarios, right? It's like changing the numbers and repeat the simulation under different conditions. This is not possible with a rule of thumb, right? So here I'm proposing this this catchment close to Falcade. Some of you know this place very well. The plant is, we don't know, maybe under construction. They are along the way. The proposed capacity is 0.15 cubic meter per second, about 1 million kilowatt hour per year. Net present value of 1.5 million euros with about 230,000 euros per year of revenues. This is the flow duration curve, natural, workable flows. So the red line is about the flows that you process in the plant, and the the light blue is what happens downstream. Now you change the scenario, you see lower hydraulic head and wider catchment. So you place, if you look at the picture, you place the intake a little bit downstream. Why it could be useful? The larger the catchment, the larger the queue. So you can process more water because now the catchment is larger, 4.78 instead of 4.13. What is the price that you have to pay? Provided that the intake is downstream, the head is reduced from 203 meters to 198. So you lose 5 meters of head. It is worthwhile? We don't know. You do all the systematic analysis, assuming the same type of plant, the same flow duration curve. You run the simulation, you derive the optimal Q under the new conditions, and you answer this question. You see, yes, now the net present value is 1.8 million euros, and the annual proceeds are 270,000 euros per year before you get 230. So yes, it's definitely worthwhile according to the data we have. It's a single Python tuning, I guess, in this case. Okay, and the same thing you can try to figure out if the type of tubing is the most appropriate. You run different scenarios with different types of tubings, changing the efficiency curve. And if you change the efficiency curve, the optimal capacity changes automatically in the procedure. Okay, and here there is a comparison about two different types of tubings. Okay, last problem related to that, and related to the question I have done a few minutes ago. Is it better a big plant or 10 small plants? Okay, the problem is the fact that the intake and the outflow are far apart, and in all the structures between the intake and the outflow, you have some rivers with a completely altered flow regime. It's not the natural river, it's something very different. Okay, this is very interesting to me. It's okay, the usual comparison, so stream flow distributions. So you have discharges, specific discharges by unit catchment area, so centimeter by day. Okay, you multiply by the area and you get cubic meter per second if you want. The red lines in both cases is the natural flow regime, what you have in the river, based on the stochasticity of rainfall and blah 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 blah. Modulated by soil moisture dynamics, sharp increase of discharge and recessions. Okay, this is the natural flow regime, flow frequency distribution, telling you that you have a gradual changes in the frequency in the range 0.05 centimeter per day up to 0.25 centimeter per day, with a slight variability in the frequency, and the most frequent flows are around 0.13 centimeter per day. Okay, that's what you have in the unregulated system. Then these two guys, I have on purpose plotted the discharge in terms of specific catchment area, because these two guys are very different. On the right, you have the Valfreda Creek, 5 square kilometers run-of-river hydropower plant, a small run-of-river hydropower plant, so small catchment, small hydropower. And on the left side, you have the Cordevole River, 700 square kilometers. So the catchment on the left is 2 orders of magnitude, maybe even more, larger than the one on the right. Okay, you don't see this because I'm plotting discharge divided by the area. This is the Cordevole River downstream of 3 big reservoirs with millions of cubic meters of storage. Okay, the last thing are the dots. The dots are what you see in terms of frequency distribution of discharges downstream of the intake. Okay, so what you see because of the regulation, because of the dams for the Cordevole River, because of a small hydropower plant, only one, small, on the right. What you see is that more or less the effect on the flow regime is the same. The only difference is the lake, the storage, and the scale of the problem. This is a small catchment, and this disturbance is produced only between the inflow and the outflow. This is a large catchment, and this impact is maybe produced in all the stretches downstream of the dam, thanks to the storage. Because the catchment is large, you could not produce this type of disturbance in the absence of a storage, of a dam. 3 in these cases. But the functioning of the system is actually the same. Most of the time you have the minimum flow discharge. And then you don't have the gradual variability of the frequencies associated to different flow magnitudes, but you have preferential states. The minimum flow discharge or some high flows here, 0.1 or 0.2 centimeter per day. And this is the case. You have minimum flow discharge most of the time, a similar minimum flow discharge, and then you have some high flows, 0.1, 0.15 centimeter per day. What is this? High flows bypassing the plant. When the plant is at the maximum capacity, you release the exceedance downstream, producing this haze. You see it. And the same thing here. And the super interesting thing is that on the right, the price of the energy is, depending on the years, let's say from 120 and 260 euros by megawatt hour, because it is renewable energy, incentives. All of us, we are paying for this. This is not energy, hydroelectric energy, not renewable, so without the incentives, based on the free market. And the price is 90 euros by megawatt hours. So there is a factor of 3 in some cases. Okay, this is the initial tariff that's dependent on the size or whatever of the plant. So maybe 10 years ago it was closer to the higher limit here. Now it's moving closer to the lower limit, but still it's impressive. This is as sustainable as a dam. The only difference is the lake and the scale of the problem. Super interesting, renewable energy. So, and again, this picture that I have already shown to you, this is a large-scale problem, even though small hydropower plants are small hydropower plants. Why? Because there are many, hundreds of them. So all the red stretches are impacted by water obstructions because of run-of-river hydropower plants. This was done 5 to 6 years ago, only considering the plants already approved or under construction or constructed. So it's maybe not up to date. The mean length of impacted reaches is 1.52 kilometers, and you generate a cumulative effect that is actually producing large-scale effects on the entire country, modifying flow regimes, modifying ecosystem services associated to streams, modifying stream connectivity for fishes, modifying vegetation dynamics for riparian vegetation that is strongly related to the frequency of flooding and droughts in the stream, in the riverbed, modifying dynamics of invertebrates and the entire food web of the river itself. Okay, I think that's it. So I have 2 classes more. I will be talking about some issues associated to the authorization procedure and the management of small hydropower plants. And then there is the last class about the homework associated to this, where you should have to find out the optimal capacity for a run-of-river hydropower plant based on some data. Okay, see you tomorrow.